Okay, Kiitos. All right. So I'm going to talk to you about the idea of extracting technology metals from waste. I'm going to talk to you about technology metals. These metals are what we need to drive our technology. Current manufacture needs materials and metals at a very high degree of purity, but supply of these metals is inefficient, expensive, and currently happens at a very small scale. Environmental laws in Europe make recycling of many of these metals not viable, and most sources of technology metals is mining and recycling outside Europe. On another front, 3D printing needs very pure feedstock in fine powder, and nanotechnology requires very, very pure feedstock. I'm going to bring these ideas together in this one idea. What we call recycling at the moment is done quite well for some metals. Aluminium, iron, copper, for example. On the left you see the periodic table, and the colour code is how well we recycle these things. The white is we have no information at all. The red is that we are recycling less than 1%. And you may notice that is where a lot of our exotic metals are to make things like iPhones. So most technology metals are not recycled well, if at all. And what is recycled almost always has high impurities in the products. And when we do recycle, we need hydrometallurgy to do this. And due to the nature of this, it's not done here in Europe, and it's actually not legal in some cases because of the chemicals involved, so it's usually done somewhere else. Most of the time, we are sourcing these materials from mining. Now here's the periodic table again. In red, it's something that has a serious threat in the next 100 years in terms of current supply. In orange, there is a limited availability future risk, and green is abundant. You may notice our technology minerals have supply risk. 80% of material consumed comes from the ground, and almost all metal sources come from outside Europe. And most technology metals are produced as a byproduct of something else with a very poor efficiency. So across to 3D printing, metals can be used now. This will all be pulled together. Powder is the most versatile form for 3D printing. Very fine is better. Sourcing that feedstock at the needed purity has been very difficult. And that bottleneck needs to be resolved if 3D printing is going to be a viable technology. This idea I'm about to present could facilitate 3D printing done with all technology metals. Nanotechnology, the use of atomic or molecular scale building blocks for industrial purposes, needs very super pure and very small feedstock, and is currently limited by what can be used and manufactured. What if we could 3D print nanotech materials with all metals and materials in the periodic table? Watch this. We'll start with a non-ferrous waste stream with 99% useful technology metals, for example, your mobile phone. Turn it into a fully ionized plasma gas. Separate ions in that plasma gas by atomic mass and atomic charge. Capture the separate ions in different atomic mass into separate bins, and feed that into pure metal powders for 3D printing. That is the idea of Plasmagmet. So what is plasma? Plasma is the fourth state of matter. It consists of a gas of ions that have been stripped of their electrons. It's made by applying very, very large amounts of heat or a very strong magnetic field. So we'll take an atom in a gas, and we'll apply more heat and energy to it to the point where the electrons are stripped away, leaving just the gas molecule. There is technology in place at the moment. This is Sintef in Norway have made this rotary furnace with a plasma torch. If we could re-engineer this to produce a fully ionized gas stream. So we're going to take a solid, let's say shredded bits of mobile phone, and turn it into a plasma. We will take that plasma gas and then we will separate it. I will do it by taking a conventional mass spectrometer and re-engineer it. Now, mass spectrometer splits things up in terms of mass to charge ratio of ions. And that's how we characterize things. What if we use that to separate things into separate bins? So, we take our phone, we put it into a furnace, we turn it into a plasma gas. We put it through an electromagnetic field, and what is then captured at the other end are very, very small, very, very pure different parts of the periodic table, which are then fed into 3D printing stock. Challenge 1, characterize the plasma furnace and its output. Challenge 2, how strong does the magnetic field need to be? Challenge 3, how do we capture those ions separately? Challenge 4, control what stable elements the ions turn into. This is the concept of the maker, for those of you who have watched Star Trek. We'll take rubbish, put it in one end. Ferrous metal scrap. Yes, I like it too. We'll put it into our device. Nano pure metals come out the other end, is fed into a 3D printer, which makes technology products. Some of them could be really small if we can get the printer to work properly. So waste disposal, metal resourcing, and manufacture is now all done in the same place. It could be done here. And it could trigger a materials revolution in manufacturing. And if that happens, what information, according to a 3D printer design, is actually more valuable than the materials itself? Power consumption will be a problem. This idea will consume an enormous amount of power. Then again, take your phone out and look at it. What was the net energy used to explore, mine, process, refine, smelt and manufacture the materials to use to make that phone? And if you did an audit, you'll find an enormous amount of energy has gone in to make that phone. So is it really inefficient? And if it is more, well, this idea could source materials at a purity and fine size for an exotic metals and materials that is currently not possible. So the process at the moment is develop the technology feasibility first, then examine viability second. What is needed in closing? Stages of development are develop theoretical concept, demonstrate at the laboratory scale, and then make a pilot. Partners to find, and this is what I need to do now. Find a good physics department that understands plasma, electromagnetic fields, and ion chemistry. Find a partner that can engineer different kinds of instrumentation. Find a patron to back the idea and funding. Find a partner that can engineer plasmic furnaces. And this is what I want from this meeting. Benefits and impact. Chemical-free extraction of high purity metals of all kinds from waste. We could recycle 100% of metal alloys and electroplated feedstock. We could revolutionize 3D printing and or nanotechnology. Very little waste plume, if any. We can take the problem waste and turn it into a much needed metal source, and we can reduce our dependence on Chinese metal sources. And the whole manufacturing lifestyle can completely restructure into a closed loop, and this has the capacity to resolve toxic waste disposal issues like nuclear waste and asbestos. Kiitos.
Thank you, Simon. Very, very interesting and inspiring presentation. I assume that a lot of this has been done outside of the 6-week period, or has it been done?
This is an idea I've had 10 years ago, and I've been looking for a person to give it to. Would you like it?
Yeah, if I had the skills necessary, I think it's really a fascinating idea. And I mean, you're really capturing in this small set of slides in 7 minutes a concept that, as you say, could disrupt this whole chain. And the periodic table you show with the limit on the available metals and non-metals that we're relying on these days is scary.
Yes.
It is.
It's a game changer.
Yeah, absolutely, absolutely. Were there any, I've been checking online, and although you've made it clear what you're looking for, I think we will have to hope that someone in the chat will respond immediately. But as said, all of these presentations will be recorded, or have been recorded, yes, and then will be available, so they will be available online. But Inga, did you have a question? You were poised with the microphone.
Thanks, Simon. Have you thought about the cost side of the technology and the
cost?
Yes.
A little, yes. It will be a lot. I have been talking to a corporation about what it would cost. We are up in the millions, right? Their comment was we would probably need something like 10 million euro to make the pilot if we get that far, right? So we are talking about a considerable amount of waste. However, the prize is the market that would come from that is extraordinary. And where they see it is get this, the space industry up in orbit, where 3D printing is done in orbit. That is where the industry would revolutionize this idea, and the money associated with it is measured in hundreds of billions. So if we are successful, a couple of tens of millions for concept is not a problem. The problem is, can we jump that hurdle? And at the moment, that's a very scary number. If I asked you for 10 million euro, would you give it to me? So, yeah, exactly.
But yeah, I mean, you're absolutely right. When you think about it from a sort of space technology point of view, it's not that much at all. but the sort of numbers that we are thinking about, it probably is a threshold. But I was just going to go on and say that, you know, when you started talking about the space thing, it brought me back to the Star Trek reference again. So we've actually closed that loop as well, which is rather nice in a presentation.
This is why we watch Star Trek.
Very good.
Another question.
Hello, thank you for the nice presentation. Just a little bit to get concrete references. Can you estimate how much energy would you need to kind of separate the cell phone, for instance, into?
I did some thumbnail back of the envelope. We are talking about 20 to 30 megawatts, right? And we won't vaporize all elements, we'll vaporize some. So let's say I'll walk you into my lab in however many years' time, and I'll say, give me your phone. And foolishly, you'll give me your phone and never see it again. I'll put it into the machine, we'll shred it up and we'll vaporize it, but not all of it will be turned into a gas. Only some, because different things have a different melting temperature and they have a different gaseous temperature and different plasma phase. So some elements will go through. We won't need to vaporize the whole thing. Like if we went all the way up to like a really, really high temperature, yes, we could do it all. But elements like tungsten require a colossal amount of energy to get that far, but some of the other elements do not. So we need to do a theoretical conceptual study. Can we get some of these elements at a lower temperature? And if the answer is yes, then we won't necessarily need 30 megawatts. We could get away with 15 megawatts. But we are talking about an industrial site like that.
Okay. Thank you so much, Simon. We need to move on in interest of time, but it's really, really very interesting. Thank you so much.